Hello and welcome. In this video, we're going to prove the derivative shortcuts for exponential functions and logarithmic functions. So let's start with the derivative of e to the x, which we know to be e to the x. But why is that? Well, before we start the proof, we're going to need this limit. The limit as h approaches 0 of e to the h minus 1 over h. We're going to want to know that that's equal to 1. This limit sometimes is just taken to be the definition of e. So e is the number that happens to satisfy the limit as h approaches 0 of e to the h minus 1 over h is equal to 1. But other people have different starting points, or there are other ways where you can start by defining e in a different way. But assuming that it's taken as definitional, we will take it as definitional. E is the number that satisfies this limit. So with that under our belt, we can say that the derivative of e to the x by the limit definition of the derivative is the limit as h approaches 0 of f of x plus h, which looks like e to the x plus h, minus f of x, which looks like e to the x, all over h. We can break up e to the x plus h into e to the x times e to the h, and then factor out an e to the x from each of the terms on top to get e to the x times e to the h minus 1, all over h inside. Now the e to the x is a constant with respect to this limit, right? All we're doing is making h approach 0. E to the x is not changing at all. So we could even pull that out of the limit altogether if we wanted to, and just focus on the limit as h approaches 0 of e to the h minus 1 over h, which we said was equal to 1. So we get e to the x times 1, which is just e to the x. So that proves that the derivative of e to the x is e to the x by the limit definition. Now how do you get the derivatives of the other base exponentials? Well, rather than going back to the limit definition again, what we could do is make use of the fact that we know that the derivative of e to the x is e to the x, and we could rewrite a to the x, which is, again, a represents any base, any constant, or, well, at least greater than 0 and not equal to 1, to be precise. So we can rewrite that a using an exponential with base e. We can rewrite a as e to the ln of a. This is the same thing as a because the exponential base e and the log base e here would undo each other, and you would get a if we wanted to go in reverse. So it's a little bit strange at first that we're complicating it by writing a as e to the natural log of a, but this occurs in other places in mathematics as well. So e to the ln a is, again, just a representation of a. So you still have that power of x there on the top. Now, what we could do with these powers is then take the ln a and the x and multiply these powers together. I mean, if you'd have something raised to an exponent, that whole thing then raised to another exponent, you can multiply the exponents. Just as a property of exponents. So you can write it as e to the x ln a. Now, if you take the derivative of e to the x ln a, there you can use the chain rule to figure out that derivative. You'll have the derivative of the outer function, which is the exponential base e function that we just proved a moment ago. So it's itself, leaving the inside alone. So you'll have e to the x ln a. That's like the derivative of the outer function, leaving the inside alone. And then times the derivative of the inner function. So times the derivative of x ln a, which is just ln a, just that constant coefficient ln a. Now we can go back from e to the x ln a and rewrite that back as a to the x, and we've got the right-hand side of our derivative of a to the x, which is a to the x times ln a. So that shows that the derivative of a to the x is a to the x ln a. So the ln a is actually popping out because of the chain rule, it turns out, at least going through this version of the proof. So those are exponential functions. Let's take a look at logarithmic functions. It turns out that for logarithmic functions, we can use implicit differentiation to help us prove the derivative shortcuts for logarithms. Let's start with ln x. The derivative of ln x, remember, is 1 over x. So we're going to start by writing y equals ln x. And we're going to try to solve or get rid of the log to rewrite it using an exponential, because we know what the derivatives of the exponentials are. So let's try to use those facts to help us take the derivatives of the inverse of those exponentials, which are the logs. So the way we can do that is rewrite this using an exponential kind of format. And we can do that by applying the exponential function to both sides, which gets rid of the logarithm on the right side of the equation. So we don't have logs. And now what we'll do is we'll take the derivative of both sides with respect to x. Here we'll be able to take the derivative because we know how to take the derivative of an exponential. We just proved that a moment ago. So we're going to take the derivative of both sides with respect to, technical difficulty, with respect to x. Let's just take that in a separate step. So we have e to the y equals x, and what we'll do is we'll write the derivative with respect to x on both sides, just to show in a separate step that we're taking the derivative of both sides with respect to x. Now we're going to have to use implicit differentiation because the variable x here is different from the variable y here. So this is going to involve a chain rule. We have derivative of the outer function, which is the exponential itself, right? The derivative of the exponential is the exponential with base e at least. And we got to leave the inside alone, but then we have to multiply by the chain rule by the derivative of the inside with respect to x. So the derivative of y with respect to x. On the right side we just get 1. And now we can find dy dx. We're trying to figure out what dy dx is and hopefully show that it's equal to 1 over x. Well, we'll divide the e to the y over, try to rewrite this in terms of x. Remember that originally y was equal to ln of x, so we have e to the ln x. But like we were saying a moment ago, e to the ln, those are going to undo each other. So e to the ln x will just be x. And so we've arrived at 1 over x, which is great. So that proves that the derivative of ln x is equal to 1 over x. We can extend our result, it turns out, to include negative x values. So in general, the derivative of ln of the absolute value of x is also equal to 1 over x, for x not equal to 0, of course. X equal to 0 would make ln undefined, and it would put 1 over 0, which would be all bad. So this is true as long as x is not equal to 0. So this handles then both positive x values and negative x values. It extends the domain of the logarithm so that it could take positive or negative values. And that's because we put these absolute value bars in here, which makes the input always positive. Now you might wonder why we're talking about this, and the reason is that down the road this semester we're going to look at reversing the process of the derivative, and that's going to be called integration or anti-differentiation. And that process, if we want to anti-differentiate for the most general possible x values, when we anti-differentiate 1 over x, we're going to write ln of the absolute value of x rather than just ln x, so that we can use the most range of x values that we possibly can. So that's just a little subtle side note, really, but something that will be important down the road. So here's how to get the derivative of y equals log base a of x. So not just base e, which is what the natural logarithm was, but base a, which could be any other base. Well, similar to how we dealt with a different base for the exponential function, we're going to turn the log base a into natural logarithms here. And the way we can do that is by the change of base formula. Change of base formula allows you to take a log of any base and convert it into a log of any other base. And the base that we know about and we just proved was the base e logarithm, the natural log. So we can write log base a of x as ln x over ln a by the change of base formula. And now to take the derivative, it looks like we might want to use the quotient rule, but ln a is a constant, and so we can pull that constant out in front as a 1 over ln a, right? This ln a is on the bottom of a fraction, so it's really like a 1 over ln a that we can pull out in front of the derivative. Because 1 over ln a is a constant, at least with respect to x. So we have 1 over ln a times the derivative of ln x, and the derivative of ln x we just proved a moment ago was 1 over x. So multiplying these two together, we get 1 over x ln a, which is exactly our derivative shortcut for log base a of x. So those are the derivatives of exponentials and of logarithms. Thank you for watching, and see you in the next video.